And the next speaker is Konrad Tristram from ISO. We will talk again about Circinus, but in a different wavelength range.
Hello, I hope you can hear me and see the slides. Quick confirmation, please.
Yes.
Okay, great, thank you. So thank you for organizing this very interesting conference and for giving me the opportunity to present this work here. I regret very much for not having been able to travel to Exeter myself as originally planned, so I fear I have to give it remotely and not be there in person. So after the great introduction by both Violetta on AGN more in general and what optical infrared interferometry can do, and also what has been presented on the Circinus galaxy specifically by Jacob, I'm not going to put too much emphasis, or I'm not going to stay with any introduction. I'm going to jump right away on getting a complementary view on what we have just seen for the Circinus galaxy in the infrared, what ALMA sees for exactly this galaxy on comparable scales. We're not reaching exactly those scales, but we are at comparatively well scales. So Circinus has actually been observed previously by ALMA. There have been observations with high resolution, let's say. There have been first observations already in cycle 1, published back in 2013, which were aimed at the detection of H2O water maser, which are shown here by these contours. But also at the frequency observed, 321 gigahertz, which is about roughly 900 micron, if I remember correctly. You see this kind of extended structure up here, one-armed spiral, like an arm, like a Popeye arm, almost going to the northeast. Then later, there has been some work published by Takuma Izumi, which observed a molecular transition in the CO3 to 2 transition, as well as the atomic C1 emission line. And here the CO3 to 2 shows that it's actually not centered. So the highest peak seems not to be centered on the nucleus, which is shown here by the cross, determined from the continuum emission. But seems to be offset. That was one of the detections, and by comparing the CO emission and the C1 emission, this was interpreted as signs for the radiation-driven fountain model, which was actually the picture shown by of the more complicated picture of what we imagine the torus looks like is actually from this Izumi 2018 paper, which was shown by Jacob in his talk. But as I said, the peak is not on the nucleus for the CO, which was interpreted by Takuma Izumi as evidence for destruction of molecules at the center due to the harsh X-ray radiation. Now, for our observations, we focused on band 7 and band 9, targeting 2 CO transitions. Here in the bottom, you have the so-called CO ladder observed with apex in a very large beam focused on the center of the galaxy at 45 arc seconds. And you have the different quantum states, transitions of the CO emission down here on the bottom with the line intensity on the vertical axis. And you see that you have like a peak around the fourth and fifth quantum number, and the 2 lines we are focusing on is the CO3 to 2 transition, as well as the which is at 345 gigahertz, which corresponds to 868 micron, and CO6 to 5 at 691 gigahertz, which corresponds to 434 emission. And of course, we also get continuum emission with this. And we do have some detection of additional emission lines, HCN and HCO, which are dense gas tracers, but I'm not going to specifically focus on these due to the time constraint of the talk. So for the remainder of the talk, I will focus first on the continuum emission, the information we can derive from the continuum emission, the morphology, and where the emission actually comes from, the emission mechanism. And then I will go to the CO lines and the kinematics of the nuclear region, and also on the hole that I was mentioning. So here you see the band 7, 870 micron emission, where you see clearly a strong enhancement towards the nucleus, almost like a unresolved point source with some extended emission. And this arm up here is exactly this arm which was already seen by Hagiwara with a size of 1 to 1.5 arc second, like an S-shaped structure. You see also some vague emission towards the south, which is clear in the molecular lines, but it's there. Now there's here overplotted now the contour lines, where we have, which I will plot also in the following plots, just as a reference, always taking these contour lines from the band 7, 870 micron continuum. We have here now the band 9 data, and you see that we have roughly the same morphology with the central source and some extended this arm structure towards the northeast. So we find this S-shaped morphology plus a core. We can do some simple image analysis on this core, which is where we have of course, the beam is larger with the 900 or 870 micron data than the 430 micron. And we find deconvolved size of essentially that for the band 7 data is essentially unresolved, much smaller deconvolved size than the beam, while for the band 9 we see that it is slightly resolved, which corresponds to a size of 3.2 times 2.2 parsecs, slightly elongated, as you can see here on the right without the contours, along what we would call the disk axis, as already presented in Jacob's presentation. The beam is, as you can see below here, the beams are also elongated in this direction. So I would not bet my life on this, but there's at least some indication that we are seeing some extension along the so-called disk axis for the central source. What is a bit strange is that the longer wavelength emission seems to be more compact than the shorter wavelength emission. Normally, one would expect that the cooler dust cooler dust would be more extended, and therefore we would get more extended emission. So to kind of look a bit more at the emission, what's the source of the emission mechanisms behind, one has to think what are the typical emission mechanisms we have in the submillimeter. And there's 3 of them which have characteristic power law spectral indices. There's, of course, thermal dust emission, which has a power law spectral index typically between 3 and 4. Then we have free emission, which has a power law spectral index of -0.1. And then there is also synchrotron emission, which has a power law spectral index of -0.7. And now if we do a flux ratio map of the continuum emission from band 9 to band 7, you see here on the right, you see that the extended emission has roughly a flux ratio of higher than 10, which corresponds to a spectral index between 3 and 4.3, which clearly indicates or is an indication for this to be emission of dust. For ALMA speak, this would be warm dust. Of course, for infrared speak, this would be relatively cool dust around 100 Kelvin and so on. Now, you clearly see that at the center, we have a much lower ratio below 4, and this corresponds to a spectral index of 2, and might indicate indeed that there is a different origin of this emission. Clearly, there's something different going on in this nuclear point source than in the extended emission. So to take another look at this is to take a look at the spectral energy distribution. This here is the spectral energy distribution with the wavelength at the bottom and the flux on the vertical axis. The blue points are high resolution data, sub-arc second photometry of the source here in the infrared regime, here in the submillimeter regime, and here in the radio regime on the right. The cyan crosses are low resolution data up here, for example, from IRAS. And what you can see, the SED is composed essentially of two areas. On the left, you have like this big bump. And here on the right, you have this kind of more or less possibly linear regime. So the left, first, just before I go to the nucleus, here just for comparison, this is the dust on the spiral area, where we have the spectral index of roughly 4, and you see this is the emission from the Rayleigh Jeans part of dust here. For the big bump, this is of course dust emission from the so-called torus. And here in red, I plot the model from Marko Stalewski's paper 2019, where actually Jacob, in his presentation in the first or second slide, showed the model of this clumpy disk with a hyperboloid polar extension. So this is exactly the spectral energy distribution here in red, shown for this model, which was fitted to the MIDI data as well as to the spectral energy distribution without taking care at that time of the ALMA data, which is here around 1 millimeter. And we see that the ALMA data is all lying above this model, which is good because the model is fine. We don't have any problem with it. And we actually have some room for some additional even cooler dust or some other emission coming from further out or from other regions. Here and then at the longer wavelength range, we essentially have a power law distribution, which we can fit with a power law index of -0.4. And our preferred interpretation for this would be like similarly to what there is present in 1068, to this to be free emission. But it means, or it implies, that for these points here, which are actually the band 7 data at 300 around 345 gigahertz, that we have actually a significant contribution to the emission from this non-thermal, non-dust emission component, which is on the order of a quarter to half of the emission. And this nicely explains the different spectral index we see at the nucleus, but it also might explain to some part that the source appears much more compact at these longer wavelengths than in the band 9 data at shorter wavelengths. Okay, so nevertheless, let's take a comparison now to the mid-infrared data. Unfortunately, the ALMA data we have so far, which is here now the best resolution data we have so far.
2 minutes, Konrad.
Sorry?
2 minutes.
Okay. Does not match exactly the spatial resolution of Matisse and MIDI, but here you see on the left again the band 7 data, and on the right you have the Vizier image, which is a bit on larger scales, but you see also this polar emission on even larger scales, out to 1 arcsecond scales, where here the nuclear point source was subtracted. Here is kind of the image that was presented by Jacob here in the center. It's just only a very central part. And if we overplot the contours from the ALMA data, we see that we are looking at two very different dust components here. So the hot or warm dust from the infrared versus the cold dust from ALMA. Okay. Just very quickly now in the last 1 or 2 minutes, the line emission. So here on the left, you see the CO322 emission, and on the right, the CO625 emission. If I take away the contours, you can see that there is indeed no enhancement towards the center in the CO322. We see the big spiral shape. The shapes are similar to the continuum, but you don't see the clear peak, while you do see a peak in the CO625. So contrary to that, the CO is destroyed by a harsh X-ray radiation. I think the more likely interpretation is that the CO is excited to higher excitation levels, or for CO 3 to 2, we are looking at self-absorption towards the nucleus. The line emission also allows us to look at the kinematics, and the kinematics, as you can see here, for both these lines and also for the other lines we have detected, is clearly dominated by rotation without any significant signs of or the necessity for outflows. If we fit simple ring fit models to the data, as you can see here on the left for the CO 3 to 2, that's the fit, while on the right you have the residual. There might be some indications for a slight outflow here, as you can see the blue shifted part to the north and the red shifted part to the south. If we take these velocities, we can get both the rotational velocities here as a function of the radius, which are between 70 and 130 kilometers per second, while the velocity dispersion is typically less than 30 kilometers per second. And with this, we can estimate the scale height of the disk on scales of 10 parsecs, assuming one self-gravitating thin disk. We get an H/R of 10%, so relatively thin disk, and assuming hydrostatical equilibrium, we get an H/R of less than 0.3, which implies that the main obscuration and collimation, which actually requires an H/R, the collimation of the ionization cone to an opening angle of about 100 degrees, requires an H/R on the level of 1, must be on sub-parsec scales. And this remains you with the conclusion of what ALMA can kind of contribute to this picture of the Circinus galaxy. So the dust continuum, we see a cool dust, probably tracing the midplane of the disk with no polar dust extension, clearly showing that we are seeing two different components, dust components, with the infrared data and the ALMA data. So it's not just a continuous one component. We are probing at these two different wavelengths. We have non-dust emission contaminating our band 7 data, so longer wavelength data in ALMA, and the molecular material is clearly dense and possibly excited to higher transitions for the CO transition towards the nucleus. It's dominated by rotation, and the disk on 10 parsec scales is too thin for the collimation of the ionization cone. So the collimation has to take place on smaller structures, parsec scale structures, which are actually the ones probed by the infrared interferometry. Thank you.
Thank you.
Question.
Time for one short question. Online questions. Jacob?
Yeah. I hope it's a short question. Do you have any guess where this hot dust goes as it's ejected out? Because it has to cool somewhere. So I mean, what are you guessing is happening that's leading to these two basically different regimes, rather than some like radiation fountain of dust cooling and being seen in these cooler dust components that you're probing with ALMA? Like, do you have any guess for like why it's not showing up?
So I think, as you can see from the spectral energy distribution, we just probably have not reached, I think we have to go deeper essentially. So if I go back, if I go back here, so you see, so the red is the polar dust, essentially, or dominated also by the polar dust from what we are seeing. So if we go like, I don't know, 2 decks deeper in with ALMA, we also have to start seeing this red part at some point. So that's my first guess. So, but it's not there is another component which is kind of filling up between the red curve and the blue points here, which is very dense and much cooler dust, which is not really seen in the mid-infrared, which is in the mid, that's my interpretation, in the mid plane of the disk, which is totally dominating what we are seeing with ALMA. And that's why we are not seeing any of this polar dust with ALMA so far. Yeah, it's a good question but that's from the Vizier or from also the spectroscopy of, what was it, Pat Roche, I think. You can see that all the way out to 1 arc second, the temperature of the dust is not really dramatically going down. So that's an open riddle for me and you to solve. Why we don't see such a strong gradient in polar direction of the temperature as you have nicely shown there is in the disk direction.
Thank you.
Okay, thank you. Let's thanks again to Konrad.